Hello, uh, I'm talking now about section 7.5, strategy for integration. The problem is when you see some integral, not in some special section, but just integral given by itself without any other indication, how to select a method for solving. I need to tell you right away, the best strategy is to have more practice. With more practice, you will learn how to recognize the type of the integral and what exactly a tool to use to solve it. Will it be substitution? Will it be integration by parts? These things are learned best by practice, personal experience. Nevertheless, I want to repeat some standard positions here, and I will solve several integrals and discuss the method. Here I want to start with this example. Integral from 1 to 2, and inside we have natural log x divided by square root of x dx. How to approach it? Well, I have written, and I have mentioned before when we did integration by parts, that integrals that have logarithms or arctangent or arcsines, they are usually done by parts, and one of the functions is the one that we differentiate is taken to be the logarithm, so it will disappear. So here again is the formula for integration by parts. If you have integral with limits here, u dv, you go uv between a and b minus integral v du. Or written with derivatives, this will be u v prime dx equals uv from a to b minus integral u prime v dx. So u and v change places. And we want the second integral to be simpler. So for this integral, I shall take u to be natural log of x. This way u prime will be 1 over x, and you see the logarithm actually disappears. So what will be v then? V prime will be 1 over root of x. And to find v itself, we had to integrate this. So v will be antiderivative of this. I shall write x negative 1/2 dx. And this will be x plus 1/2, so square root of x, divided by 1/2, which is multiplication by 2. So that's v. I have u, I have v, and I can go and start solving this integral. So first we go uv, the product. So I shall write this first. This is v. And here logarithm x, that's u, from 1 to 2, minus integral 1 to 2. Now look, I had to multiply u prime v. So let's do it. 2 root of x over x dx. Continuing with this work, let's separate this work in the box. And first, let's evaluate the middle term. When you plug 2, you have 2 root of 2, natural log of 2. Fine. If you plug 1, you get 0 because logarithm 1 is 0. So that's what remains from the middle term. And then in this second integral, we can take 2 outside, it's a constant, and root of x over x we can reduce, because x itself we can write like root of x squared. So this integral becomes 1 to 2, 1 over root of x dx. Just this. And we already actually solved this integral. So we have 2 root of 2 natural log of 2 minus 2 times, and remember how we found v from v prime, so this will be 2 root of x between 1 and 2. Evaluating this expression, we have 2 root of 2 natural log of 2 minus, there will be 4 root of 2. Root of 2 minus 1, like 2 times 2 is 4, and then for the radical we have root of 2 minus root of 1, which is 1. And practically this is it. This number is our answer. And when we solve such integrals, we don't use decimals. I want to see the answer, exact answer, exact numbers. Exact number is root of 2, exact number is logarithm of 2. We don't replace them by decimals. Why not? Because in many cases we need these exact numbers to use them for some other purpose. If you evaluate this on a calculator, it will give you approximation. Square root of 2 is not a rational number. You cannot represent it like some exact fraction. It will be a decimal and it will be approximation, because the calculator can go like 12 digits, not more, 10 digits. Same situation with logarithm 2. It's not a rational number. This is the only way to write this value in exact form. Okay, moving to another example. Solve this integral. X 2 power x dx. We have practically exponential with x. If we have exponential with x, or sine or cosine with x, again we do integration by parts, but this time we take u to be x, so u prime will be 1. If it's x squared, again you have u is x squared, and then you have to repeat the process twice. What about 2 to the x? That's practically exponential. So here v prime will be 2x, v will be antiderivative of this. And remember how we integrate this. We can write it integral exponential x natural log of 2. So this will be exponential x natural log of 2 divided by this coefficient natural log of 2. And on the top, that's actually 2 power x, and here natural log of 2. That's how we integrate such exponentials. And now I shall solve the integral in this space that is left here. So we go uv. V is, remember, 2 to the x over natural log of 2. So I have x to the x natural log of 2. Just this term we're working antiderivative. So this is one part of the antiderivative. And then another one, now we have 2 to the x dx. U prime v. And here we have this natural log of 2, which can be taken out. And integrating 2 to the x like we just did, another logarithm 2 will come. So this will be x 2 to the x over natural log of 2 minus 2 to the x natural log of 2 squared, and we put plus c. U v prime equals uv minus u prime v. Okay, moving to another example. Now I want to work on this integral. It's from the book again. integral from 0 to root of 2 over 2 on the top. Let me make it better. Root of 2 over 2. This is the upper limit. And we have x squared over square root 1 minus x squared dx. Okay, what about this integral? When you look at this radical, square root 1 minus x squared, natural thing is to think we can do two things, either substitution or trigonometric substitution, regular u substitution or trigonometric substitution. Regular u substitution will not work because of this x squared on the top. Let me show you quickly. If you take u to be 1 minus x squared, then du will be negative 2x dx. But on the top we have x squared dx, and 1x will be left. 1x will be left and you don't know what to do with it. So we cannot rewrite the integral in terms of u entirely. I should put a question mark for this substitution, so it doesn't work. And we take a trigonometric substitution. Let's put x to be sine theta or cosine theta, doesn't matter. Then the x will be cosine theta d theta. Excellent. What about the radical? 1 minus x squared. This will be square root 1 minus sine squared theta, which will be square root cosine squared theta, which will be cosine theta. So this is in the place of the radical. Now I'm having x squared, which is sine squared theta on top. Below, radical becomes cosine theta, and the x becomes cosine theta d theta. This is very good. Cosine will reduce. Now I have to change the limits. We should not forget about the limits. Look at the equation for x and theta. When x is 0, we can actually write theta is arc sine x. When x is 0, theta is 0, so we put lower limit 0. Now when x is root of 2 over 2, what is arc sine root of 2 over 2? What is the same 1 over root of 2? Sine of what angle is this? Well, thinking about this situation, we figure out that this is pi over 4. So on the top, we have to put pi over 4. Okay, so we're going to solve this integral now. Because we have sine squared, we use the special identity. So this will be integral 0 pi over 4, 1 half, 1 minus cosine 2 theta d theta. That's how we represent sine squared. It happens very often. And then we integrate two terms here. It will be integrating 1 half, you get just theta. So this is 1 half theta between 0 and pi over 4. And minus 1 half, integrating the cosine, we have sine 2 theta over 2. Again between 0 and pi over 4. Evaluating, that's 1 half times pi over 4. 0, this is 0. Then minus 1/4 sine, here a mistake. This is pi over 4, upper limit. Okay. When theta is pi over 4, 2 times this is pi over 2. Sine pi over 2 is 1. So we have 1 and the other is 0. At the other end, it's 0. The result finally will be pi over 8 minus 1/4. So again, I want to repeat about making substitutions. You change, there are 3 steps. Change the variable to using new variable. So we have theta here. From x we go to theta. Then we compute the x in terms of the theta, changing the differential. It tells you according to which variable to integrate. And then we change the limits when we have limits. If we don't have limits, at the end we return to the original variable. It's a mistake just to work without limits here, change x to theta and just no limits and then return to x. That's messing up several things. That's not correct mathematically. Now I want to compare this integral that we just did to a similar one. Look at this. X cubed over square root 1 minus x squared dx. Again, we can do trigonometric substitution, which is fine. Setting x equals sin theta is okay. But I want to show you that in this case, the regular u substitution will work. If you set u equals 1 minus x squared, also works. How does it work? Here the u is negative 2x dx. So we can replace the x by du over negative 2x. The integral becomes, here we have this x cubed, here we have root of u below, and here we have du over negative 2x. Now, negative 1/2 can go outside, and reducing by x, we have x squared over root of u du. Are we stuck with x here? In this case, not, because if you look at the equation for u, I can solve this for x squared, and I can write x squared, this is 1 minus u. So we can write everything in terms of u, not like in the previous case. The integral becomes negative 1/2. We replace x squared by 1 minus u, and here we have root of u du. This integral is easy to solve. We shall need only power rule, because we write it this way: negative 1/2, 1 over root of u minus u over root of u du. And then this will be negative 1/2. 1 over root of u we did several times. So let's write again here negative 1/2 du and plus 1/2, two negatives. With the second term we have just u 1/2 du, reducing by 1/2. And continuing, here 1/2, u plus 1/2, adding 1, divide by 1/2, multiply by 2. Here with the second term, 1/2, u power 3/2, adding 1, multiply by 2/3, and plus c. Integration is done. Now we simplify. We can reduce by 2, so this is root of u here, plus 1/3, again reduced by 2, and this will be u 3/2 plus c. Returning to the original variable, this is, I forgot the negative sign, sorry, negative root 1 minus x squared plus 1/3, 1 minus x squared 3/2 plus c. Here, it's done. I hope that this example and the previous will teach you what is the difference between trigonometric substitution and regular u substitution, when to take the other one. U substitution is more simple, but it doesn't always work. Now, the last example for today, I want to show you this. From 1 to 4, exponential root of t power, and all this divided by root of t dt. it's almost telling you to do a substitution first. So you have to substitute this radical. We set u to be square root of t, which is t 1/2. du will be 1/2 t negative 1/2 dt, which is 1/2 dt over root of t. You see this is present in the integral, dt over root of t. So we can write dt over root of t, this is 2 times du, solving for this expression. And then we go back to the integral. This will be integral e to the u, and just 2 times du, 2 outside. Don't forget the limits. When t is 1, u is 1. When t is 4, u is 2. So that's it. The integral becomes really very simple. You just need to make the appropriate substitution at the beginning. And integrating the exponential function is the same. No change. Limits 1 to 2. So this will be 2 times exponential squared minus e. This special number e, which is approximately 2.7. It's called Euler number, the base of the natural exponential function, also base of natural logarithm. Okay, done with this example. We spent a lot of time on integrating rational functions, so I'm not repeating this. And what I want to repeat is that the best strategy of integration is to practice. With more experience, you will get the insight in these topics, how to solve integrals, and you'll learn to recognize what is the right method. Okay, goodbye.